Okay, good morning, everyone. Okay, now 9 o'clock. See, still some students haven't turned up, but not next week. Next week, everybody must be here, 10 to 9. Why? Because we want to give you the full hour to do the test. See, if you are late, you wouldn't be able to have sufficient time to solve all the problems, okay? So, 10 to 9, come here and leave all your bags, everything here in the front. Then find your seat on there in this hall, all right? Okay, so this is next week's test. And also, the test questions have already been finalized. So we have add up multi-choice questions. So for you guys, it's easy, pick up. Okay. So you got 4 multi-choice questions, and you have 2 calculation problems. You solve the problem from the analysis calculations, all right? So if you can go through the examples I have given to you during my lectures, and also to solve the tutorial questions by yourself without referring back to my slides to textbooks, then you have no problem. And you would have a big chance to get 100%, see? So next Thursday, do come here early. And also tell your friends, all right? Must be here early. Okay, let's continue. Last week, we talked about distributed energy sources. Okay, and that was very, very popular now because the renewable energy sources is being used very widely, not just in the city, also in the countryside as well. So, we have a question. Why we need the storage in our electrical power systems? Okay. Why we need it? See, everybody talk about storage. You said, hey, Dr. Su, we do need a battery because we want to take our mobile phone around, see? Well, of course, that's only very small scale of energy storage. But in our power system, we need very large scale, a large amount of energy has to be stored. Then you may ask yourself, hey, why? Maybe 30, 40 years ago, that was not an important issue, but now it gets more and more important. And a lot of energy storage schemes and energy storage techniques must be used. Okay, so this is the main answer. In our electrical systems, you produce energy. At the same time, you will consume the energy. You see? If suddenly the load increases, okay, a manufacturer switch on a big furnace, a big motor, you see, a mechanical operations just start. Then you need a lot of extra energy, right? So at that same time, almost instantaneously, your power station has to open the valve, the steam valve, okay, or open the hydro turbines and the water entrance gate, you see, to produce more energy. Because why? Energy can't be stored in a network and can't store in a very large scale. You may say, hey, Dr. we have electrical cars, okay, electrical vehicles. We can still store some energy. That's not a big scale. But in our power network, the energy fluctuation is so much, and your power stations have to respond very quickly. See? So this is a very typical example. So what you can see from here, solar power, this yellow portion is a solar power. Only during the daytime, only sunshine days, you can have very large solar power supply here, you see. And what you can see here, this portion is actually gas turbines, gas turbine power stations. They produce the power almost the same, you see, over the 24 hours. Yes?
Sorry, is this slides included recently? Are these updated slides? Because I can't find it.
Oh, you mean slides are updated?
Yes.
The slides is not inside? I think should be inside. They're on the last, from slide 34. Because the previous ones we already explained last week, distribute the energy sources. So from slide 34, you will see that. So from here, so what you can see from here, we have gas turbine, base load, we call it, supply the base load, okay? In a power network, in a big power network, for example, in Australia, all the power stations, most of them, most of the states, they connect together, you see. Even Tasmania is connected with our Victoria by the submarine cable, about 120 kilometers submarine cable. It's amazing, okay. If you have any chance to visit the substation on both sides, you will see it's very, very nice. Okay, it's very good, very big. Here, the base power is supplied here, you see. Then your daily load demand is here. This is the pink lines here. This is your demand here. The real-time load is this, the green one, see? So you can see the early in the morning, the load is very, very, very small, very low load. But during the daytime, the load pick up until quite high, and then there's a small drop here. Then at the light, okay, in the evening, the load specifically goes to the peak. Because why? Most people go home, switch on TV, switch on lights, okay, cooking, electrical stoves, okay, so that the load will pick up. Then you can see if we just use the base load, gas turbine here, then we have a big gap here, you see? Is this big gap from the demand and your supply? You have a big gap there, you see? So this gap, actually, we can use two different energy sources to compensate it or to meet the gap. Okay, one is hydropower station. Another one is energy storage. Okay, you store energy there. You can release, you can produce more energy, more power to meet the demand. Okay, and somebody may ask me, hey, Dr. Su, why your gas turbine only constant power? You can just increase the gas turbine output, right? Why not? Not easy. Gas turbine with constant power supply, constant power output, or you will have the highest efficiency. Okay, to suddenly change or reduce is not that easy. Okay, not economically acceptable, I must say. See, but hydropower station quite easy. You want to pick up the power, just open the valve, let more water come in. See, so hydro turbine is one of the important power sources to meet the peak demand. See, so here this is what we need to put on. But another thing is, we do want to have new energy storage systems, not just for the network demand, but also for distributed energy sources, you see. And for example, you have a solar panel on the roof. Then during the daytime, you have a lot of power. You use all of them. Then what you can do? But in the evening, you want to use the power saved, right? Put in the storage. So we have local small storage for the distributed energy sources and distributed customers or consumers. See? So that's why we need to use the energy storage. So this is another diagram. The base demand is here. Intermediate demand, the peak demand. You see, it is quite a big difference, from the base demand. So we need to do something. So energy storage can have quite a few things to understand. I mean, some energy can store in the fuel, stored in the heat, or stored in the hydropower station. That's what we discussed. But other ones can be more difficult to extract. For example, thermal energy. Okay, in some places you have to be very careful to build up thermal energy sources. So all these energy storage sources may not be very widely used, except the hydropower. Okay, hydropower energy storage is very useful and also very economic. Energy storage, store energy into capacitors is one thing a lot of people work very hard to store the energy in the capacitors. Also, mechanical energy stored, you can convert the electrical energy to potential energy or the other things. For example, flywheels and hydroelectric storage or some other potential energy storage. And the chemical energy storage, you can use electricity to produce hydrogen. And hydrogen can actually store some energy when you need to use it, you see. Use the fuel cell. One of the very useful energy storage system is hydro pump station. Hydro pump station, the principle is like this, right? When you need a lot of more power to meet the peak demand or even the base load, you can use the hydropower station to generate energy. But at night, early in the morning, you have a lot of energy in the network, you see. So in that case, you change the generator to the motor to pump the water to the dam, see? So the energy can be stored in the water in the dam, see? So this is a very useful and very widely used in the world as well. Another thing is capacitor energy storage systems. Now you only have very small capacitors, right? People might say, hey, capacitors not really that useful because the energy stored is so small in a scale. But when the people develop so-called supercapacitors, I mean, when they get very successful investigations, then they may be able to find supercapacitors which can store a large amount of energy. But at the moment, it's still in the research laboratories. Of course, this is the very important one, charge batteries, right? And the batteries in your car is always very useful, see? And the batteries are more and more widely used in the electric cars as well. The energy stored in the battery has got some advantages. You may straight away understand it because you can move around. Okay, it's portable. Another thing is the energy density can be very high. Okay, you have a battery, you can still drive 100 kilometers, 120 kilometers, okay, per hour. So that's fine. Okay, and also because of the new battery technologies, the batteries charging time can be significantly reduced. Not like your mobile phone, you have to charge 3-4 hours But the electric car could be half hour, charge up, you can drive another 100 kilometers. So this is very nice, okay? And this is a supercapacitors, as I mentioned before. And the energy stored in the capacitor, in fact, is this equation, okay? So it depends on the capacitance, also depends on the voltage square. So which means the higher the voltage, the larger will be energy you can store in certain capacitors. Okay, so this is another thing is superconducting magnetic energy storage. If you guys come to Monash University 20 years ago, you had a good chance to visit our electrical power engineering research project using the superconducting magnetic energy storage. And that project was supported by the government, ARC, Research Council, and also by some industry, you know. And how can we store the energy in this magnetic field? You know, magnetic field itself is energy, you see. If you have the current go through the coil, you produce magnetic field. And you can store the energy in the magnetic field. And when you need the energy, that can release, which means the current you store. Okay, you can have certain current there. And when you need the current to be used for your consumers, you can release the current. But the problem is, if you have a heavy current, if you only have 10 amperes, 5 amperes, that's very little. Not much energy stored. So you need very large current, okay? A big magnetic field to store the energy. Then how can you have very heavy current without much losses? Superconductors, okay? With superconductors, you can have very, very heavy current, but very, very little loss, okay? Or even no loss, see? So this is the system, but it's quite complicated. At this moment, no commercial applications in the world, although people are still doing a lot of investigations, okay? So this is another storage, it's called flywheel storage, using mechanical energy, okay? At very high speed rotation, and the energy will be stored inside the flying wheel. And when you need the energy, the wheel can be used to connect to gearbox. The gearbox can connect to your turbine. Then you can generate electricity, you see. It's quite mechanically it's quite a complicated system, but the energy storage is still quite promising. Okay, I don't know whether you guys know that some countries or electrical car, inside smart electrical cars, when you break a car, the energy will be stored back in the battery. Do you know that? That's a very interesting thing, right? Unfortunately, it's not widely used. And also in the aircraft, you see, very big aircraft, okay, Boeing, 373, okay, 100 tons, 200 tons, very big aircraft. When that landed, the high speed has to bring to the stop, That's a lot of energy. Currently, how can you stop your aircraft? Anybody knows? Your hydro system, you break the aircraft, and also the engine start to do the opposite way, okay, to reduce the speed and stop it, see? But in fact, the energy will be all lost. A lot of energy being lost, see? But if we can convert that mechanical energy, right, the dynamic energy into electrical energy, then you can still use it, see, still save it. So this is something we have to see. Of course, there are some advantages and shortcomings for the flywheel storage. So So this is something, okay, especially the speed wouldn't be constant, change the speed from very fast to slow down. So the turbine has to be used to cope with the different speed. So there are some advantages and disadvantages. So you guys can read through quite easily by yourself. Another thing is compressed air energy storage. If you read the news, I think earlier this year there's a news a bicycle developed in the UK. They don't use battery, they don't use anything else, but you can see there's a small cylinder attached to the bicycle, compressed air inside, you see. So that's another energy storage. So compressed air, stored energy. You can use the stored energy to drive your bicycle. Also, only very small scale. There are some shortcomings as well. So this is another way. So basically, this section just gives you some idea. A lot of details wouldn't be discussed. A lot of design, a lot of calculations, issue of the energy storage may involve a lot of analysis and calculations, but it will not be covered in this course. Compressed air energy storage, it has some problems, noise, okay, the scale and the applications all have some limitations. Easy to understand. You read through, you can easily understand this, right? Okay, a comparison between the performance and characteristics. So you can see into the scale, okay, the most promising one is the pumped hydropower station. You can have a very large scale, you have a large amount of energy stored. And the free-wheel battery, only small scale. But in terms of efficiency, free-wheel is high, battery is not bad, a pumped hydro station is also not bad, but compressed air could be much lower. See, so all these things, a comparison is here, this here. See, you can have a look there. Okay, another comparison is the stored energy, and the power output. See, the comparison. So for the batteries, the stored energy you could have in this range, but your power, release the power, and 1 megawatts at this moment, you see. But hydropower stations, you can have very large power from the top here, you see. So the speed of which all these other energy storage, super capacitors, the power stored is always limited, you see. So this is another comparison. In summary, energy storage is the increase of production of renewable energy brings the problem of supply-demand matching, because you have renewable energy, locally distributed energy sources, and you do have energy consumers also distributed. So you want to have this matching. That you need the energy storage system, especially energy storage system can reduce the losses of the energy transmission across the transmission and distribution line. Okay, so this is one thing. A number of well-established methods are available, but all have significant drawbacks. And his level led us to develop more advanced methods to convert and store large amount of energy. This is the summary. And also, the major research in the world is now directed to improving the existing method of energy storage and conversion and developing new techniques. It seems inevitable that there will always be some trade-off between energy security and cost. Okay, if you want good energy sources, you need to probably pay a lot of money. Okay, a lot of costs. Okay, so this is what we have discussed last week and we finished today for the energy storage and the energy distribution. Because I have received some feedbacks and some students really feel difficult for this course. I believe not for the general expression of the energy sources, energy distributions, renewable energies. That's not a problem for you. But only difficulties, maybe the theories, okay, the calculations, especially if you don't have electrical circuit analysis, especially the AC circuit analysis and the calculations, you see. So then you do have something very difficult, you know. Even your calculator, you may not be able to use very quickly to do complex number calculations. That's a must in your middle semester test and the final test, final examination. You must be able to use your calculator to do complex numbers calculation very quickly. So, so that's why I've decided to review some more questions. Okay, use this time before the next hour. I will just go through what I discussed about the synchronized generators. Okay, synchronized generators. In fact, I have already given you very much reduced materials delivered to you. Okay, so basically we have synchronized motors and synchronized generators, right? We don't talk about synchronized motor that much because we are more use synchronized generators, but they are so much closer related to each other. So that's why we had to discuss about synchronized motors. Synchronized motors is you supply power, so your rotor will spin. And the important thing is to understand the phasor diagrams. You have terminal voltage applied. The terminal voltage will supply current as well. You have the current this way, or this way, whichever direction. Then you produce back EMF in your motor. Because when you energize your armature, you have opposite EMF potential, we call it. So back EMF will be produced inside your generator armature. So in your armature, you have a EF here, and the phase difference between your terminal voltage and the EMF is delta, which is called torque angle. For the motors, your torque angle is always negative. Because why? Because your magnetic field, rotating field, is always leading ahead of your router. See? So this is the torque angle, and your phase, your voltage and current has a power angle. And some students haven't even learned AC circuit analysis. I doubt. I mean, I really don't know. I mean, in high school, you should learn AC circuit. But then you should understand power factor. Okay. If we tell you this generator, right, it supplies power to a load of power factor 0.8, which means cosine theta equals 0.8. And from 0.8, you can find out the power angle, theta, and theta is here. It's a phase angle between your voltage and your current. Okay? Even if you haven't learned, or you forget what you learned, the AC analysis, but you just need to know the phase angle between your voltage and current and the power factor, cosine theta. That's very important. You have to remember this. For generators, it's just a small difference. It's the inverse way. You rotate the rotor, okay, use a drive, okay. Then the magnetic field will be produced in your armature. And that also becomes a rotating field. But that rotating field is a little bit lagging behind, you see. So you have a mechanical angle between your between the rotor and your field, okay? So that angle is also called torque angle. See, there will be also, that's a mechanical angle. It's all related to torque angle, sorry. And that's because you drive the rotor, so your back EMF produced would be leading ahead of your terminal voltage. So your torque angle is always positive for generators. So everybody must remember this, okay? Torque angle for the generators is a positive because you have a drive to rotate the rotor, okay? And your field is lagging behind, see? So this is one thing I want to review. Another thing is the equivalent circuit. Once you have equivalent circuit, you write your equation wouldn't be very difficult because this equivalent circuit doesn't consist of too many components, you know. So little, only 3 components. For the motors, you have a voltage supply, terminal voltage here. You have the back EMF produced or induced in your armature. Then your armature has got a reactance, so XS. We ignore, in this equivalent circuit, we ignore the losses of the armature. So no resistance here, you see. So this is a very simple electrical circuit. So what you can see is our equation can be easily written like this. Your terminal voltage equals to this back EMF plus the voltage drop across the reactance. So what's the voltage drop across the reactance? JXSIA. So this is voltage across the reactance. And this is your back EMF. So these 2 voltages added together will be your terminal voltage. So simple, right? So once you draw the equivalent circuit, you write the equation for this equivalent for this circuit. It's not that difficult, see. But if we change the generator, the only difference is you would have the terminal connected to the load. You see the terminal connected to the load. You also drive your rotor, so you produce back EMF, you see. So this back EMF will go through your reactance to supply power to your load, connect to your terminal. You see, right? So what you can see here, this is also a very simple equivalent circuit. Why? Only 3 components. One, back EMF. Another one, armature reactance. And then terminal voltage. You see? So back EMF must be equal to terminal voltage plus the voltage across the reactance. See? So you can write the equation. Terminal voltage equals to, the back EMF equals to terminal voltage plus the voltage across the reactance. So if I move the voltage across reactance to my right-hand side of the equation, so you have this equation, the difference is only here. One difference here. See, the motor is positive and the generator is negative. You don't need to remember the equation itself or the sign itself. You just need to remember the equivalent circuit. That's my suggestion. Okay, you wouldn't make any mistakes to solve the problems. Another very, very important thing is the phase diagram analysis, because we need to derive the equation to calculate the mechanical power or the output power or the mechanical power produced in the motor or the electrical power supplied from the generator, we need to derive that. So we have to use phasor diagram. And this phasor diagram, from our analysis, we can see this height is IAXS cosine theta. And this height also equals to EF sine delta. See? And this can be found out from your mathematics, right, analysis. So from here, this equal to this, then you can derive your power is equal to Vt EF divided by XS and sine theta. So your every single phase, the power output would be proportional to sine delta. Delta is torque angle. See? Of course, your power output would be also proportional to your EF, and inversely proportional to XS. Because your terminal voltage for the motor, you apply voltage 10 kV to your terminal, so you wouldn't have any problems. I mean, the voltage, terminal voltage normally is constant. So the terminal voltage would be constant. Your reactance with your armature is also constant, all right? So in this case, your power output only depends on your torque angle and your back EMF. My back EMF is controlled by quite a few things, right? 4.44, if you remember that number, that the equation, and the number of turns, right? Rotating frequency and your maximum flux. Remember that equation? So number of turns of the armature is constant. Rotating is constant, right? Speed is constant. Then it would be magnetic bands on the flux density phi. So the flux density can be changed, right? Can be changed. Because you have a DC supply for your router. You see, your DC supply for your router can change the flux in the stator. So if you increase the DC current in your router, you increase the flux, your output power also increase. See? So this output power can be adjusted by your DC current in your router. And of course, your torque angle will also change. When you have a heavy mechanical load, my machine will have much bigger pull of the force on the router, you see. My router will resist the pull from your rotating field, so that the torque angle becomes bigger, see. So this is very simple analysis, but in my lecture slides, you see if you have the load changes, how can you change the output power to meet the load requirement, you see? So you will see the energized DC current changes, the flux changes. So a lot of analysis just based on this equation. So that's not a problem. If you have a generator, you have more or less the same story, see? Only in the opposite way, okay? So generator will drive the router, and you produce back EMF, and you supply power. Then you have the equation also very similar, except your power output is positive, you see? Your generator supply power, that's the positive, you see? Again, the output power, because your terminal voltage is constant, your reactance is constant, your output power would be dependent on back EMF and torque angle. Another thing is, with different back EMF, you would have different current. You see, the torque angle can change. Your current would also change. Your power angle, hey, torque angle, power angle, different thing, right? Power angle is the angle between your voltage and the current. See? Depends on the positive or negative power angle. Your load, your supply can be capacitive or inductive, you see. So with this energization of DC magnetic field, your torque angle can change, and your power angle especially can change from negative. You can go negative, right? In this case, negative, or you can go to positive. Your current can go this way, you see. So if your current is leading ahead of voltage, you would produce reactive power. See? Sorry. For the generator side, you would consume reactive power. See? In this case, your current is lagging behind the voltage. For generator, you produce reactive power. So generally speaking, most of the turbine generators produce real energy, okay, kilowatts, megawatts. You also produce reactive power, kilowatt hour, okay. What's the unit of reactive power? VA, right? Okay. So VAR, that's your reactive power.
Motors absorb reactive power.
Sorry?
Motors absorb reactive power and generators produce reactive power.
Which is reactive power?
Motor absorbs the reactive power.
Generator, you mean? Yeah, generator, if your power angle is negative, you produce real power, also produce reactive power, you see? But for the generator, if your power angle leads your terminal voltage, then your generator produce real power, but absorb reactive power. This situation is very rare. Only in some network, if the local reactive power is very high and the voltage is too high, the bus bar voltage is too high, they absorb the reactive power. But that's not too good. But for your motors, for your synchronized motors, normally you are inductive because you have mechanical load. And your motor, synchronized motor, has got a coil, has armature. So it's inductive. So your motor will absorb real power because you have a mechanical load on the shaft. You also absorb reactive power because you are in inductance. You have reactor of your armature, see? But in some cases, if I energize DC to your rotor, very heavily current goes through your rotor. Yes, and your motor, your synchronized motor, becomes absorb electrical energy to produce converting into mechanical energy, right? But at the same time, I produce reactive power, okay? So I supply reactive power on the terminal. So locally, the consumers connect to the same bus bar of my motor will have extra reactive power, which means the manufacturer connected, they don't need capacitors, right? A lot of manufacturers, because of the power factor, because too inductive, the power factor is only 0.6, 0.5, they absorb too much reactive power. They must have local capacitance connected to the manufacturer's bus bar to produce reactive power. Otherwise, the manufacturer's terminal voltage will be too low. And also, the power industry, the utilities, they will charge the reactive power to the factory. Why? Because I have to supply reactive power to your factory, and reactive power has to be supplied through the current, which means that I have to increase the current to your manufacturer. You have increased the current, then you have increased the losses on the transmission system, on the transmission line, distribution line, transformers, everything, the loss will increase. So my utility will say, hey, that's unfair. I have to cover my losses, so I will charge you reactive power. So the manufacturers, some countries, manufacturers, if the reactive power is too much, consume too much, the power factor drops to 0.5, 0.6, the manufacturers would have to install their capacitors. But for the synchronized motors, you don't need Okay, if you have synchronized motors, then you can generate reactive power. At the same time, you convert electricity energy to mechanical energy. You see? Is that good? One stone, two birds. Okay. Okay. Now, I want to go through this question very quickly because quite a few people said, "Oh, calculation analysis could be a little bit could be a problem for us." So I would go through this example, another example, explaining some details. So you would see. Sorry?
Can you also please go
Which lecture on this?
Yes, I'm setting up this. Yeah, it's come up. Good. Okay. So this question, this question is my lecture handouts last the second synchronized machines. Okay. So in this question is very interesting. First, the terminal voltage is 830 volts. Okay. Then it's Y connected, 60 hertz, 4 poles. So all the conditions are listed here. 4 poles. The armature reactance 0.1 J ohms. Okay, so this is ohms, and your resistance as well, armature resistance 0.015. Okay, this is very first time, right? In my lectures, I explain a lot of things without ignore the armature resistance, but this question a little bit complicated because the armature resistance is not ignored. Okay, so now, okay, so then the armature current is here. And also, it's supplied, the power factor of this generator is 0.8, and it's lagging. So from this power factor, you can work out the power angle. So cosine theta equals to 0.8, right? So you can find out the angle. Okay, so to solve this question, we also have summarized the other known other conditions. Your power fraction and windage losses is 40 kilowatts. Okay. Your core losses is 30 kilowatts. You see? All right? Okay. And also, because the power factor is 0.8, so your theta is 36.9 degrees. Your power factor, power angle is this. So from here, you can write the current, armature current straight away. You see, your armature current, complex number, armature current 693 amperes, but phase angle 6.9 degrees, right? It's amperes.
Shouldn't it be negative because it's lagging?
Sorry?
Shouldn't
Lagging,
be
right?
negative because
Yes, you're so smart. Negative here, all right? So everybody must remember this because I have the lagging behind, so my phase angle of your current has to be negative. And your voltage is, your voltage here is line voltage, right? 830. All the voltages given in the problems, in the questions, are 9 voltages, okay? So when we analyze the generators, we only use a single phase. So all the voltage has to be converted to single phase. So my single phase voltage would be 830 divided by root 3. So this will be,
127.
yeah, this would be 480 volts. And it's 0 degrees, see? It's 0 degrees, okay?
So this is our reference voltage.
Sorry?
So this is our reference voltage.
Voltage is reference voltage, yeah.
This voltage is the reference now.
Yeah, voltage, always in the generator analysis, it's recommended to use voltage as a reference. You could use the current as a reference, but it's confusing, okay? Always take the voltage phase angle as 0. Then you will see the first question. The first question is say, hey, what's the rotating speed? Everybody must be able to do it, all right? The first question, my rotating speed is 2F divided by P. See? 2 times 60 is my frequency. Okay? Divided by P4. This is rotation per second, which means 30 rotations per second, and also it is 1,800 rotations per minute. Okay? So, all right. Then, question B. Question B, it is Y connected. So how much field current must be supplied to the generator to make the terminal voltage 480 at no load, which means I open circuit. See? So in this case, IA must be equal to 0. You see, it's open circuit, and your terminal voltage is still 480 volts 0. You see. So you see that next slide. You see the voltage here. You voltage 480, right? 480. So then what's your field current here? Your field current would be 4.5 amperes here. See here? Yeah. Somebody say, hey, can we directly use any formula to calculate the current? Unfortunately, no. Because of the fair materials, it's non-linear. Relationship between your current and terminal voltage is non-linear. There's a saturation there, so you wouldn't be able to do that. So you found out that current. You found out the current would be IF from the diagram. It's 4.5 amperes. Then you see the question C, if a load of 693 amperes, 0.8 power factor lagging is connected, how much field current is required to keep the terminal voltage 830 volts? So this question, to keep this voltage, to keep the terminal voltage still, okay, phase voltage still 480 volts, then you will have this equation, because here is a generator. So your EF would be terminal voltage fed plus the R, your R of your armature current, and plus JXS armature current, right? So your voltage across reactance as well as resistance. So that's your total voltage. So this all added together, it would be your back EMF. So what you can have here, this will be 480, okay? This is 0 degree plus RS is 0.015 plus J 0.1 multiplied by IA is 693 minus 36.9. Okay, so that's the equation you have here, and from this equation you calculate. So eventually you found out your EF. Your EF would be 532, 5.3 volts. Then what would be your magnetizing current? Again, you have to go to the diagram. So your terminal voltage is now 532. your terminal voltage will be 532. If I use this curve, I would be able to find out the current is 5 something, right? So my current actually is 5.7 amperes here. See? So my field current will be 5.7 amperes. Okay. So this question actually is very practical because you use all the test results, in the interchain. So D is how much power is the generator supplying? How much power is supplied to the generator from the prime mover? And what is the machine's off-road efficiency? So this question is a little bit long, right? So your power output will be equal to 3 times of terminal voltage IA and the cosine theta, you see? Your cosine theta is already 36.9 degrees. Oh, okay, so this would be 3 times 480 times 693 times cosine 36.9. So you would get 798 kilowatts. Okay. Then your copper losses is 3 times of I square resistance RS. RS is your resistance, right? So that would be 3 times current 693 square times the resistance 0.015. So the power losses would be 21.6 kilowatts. You see? So your total input power, input will be your total, will be your output plus your copper losses. Okay. Plus your copper losses plus your core losses already been given, right? The core losses plus your fraction and windage losses. So, sorry? The core losses is already been given there, you see? The core loss is 30 kilowatts.
There are stray losses as well.
Ignore, right? The stray losses.
Yes, all this.
It's not given.
Correct. All the losses, okay, fraction losses and windage losses, that's 3 phase. You can't say, hey, single phase, of course. So that's 3 phase, yeah. So here you add them together, you would have the total 889.6 kilowatts, you see. So your efficiency would be your output 798 divided by 889.6, that will be 89.8%. Okay, 89.8%. So that's your, and the question E is what will be the terminal voltage when the load is suddenly drop off? Okay, E. So if it is suddenly drop off, because your terminal voltage, phase voltage will be exactly the same as your back EMF. See? So that will be 532 volts. Because suddenly drop, my magnetic field can't change instantaneously. You see? My driver can't change instantaneously. So my terminal voltage would be exactly the same as my back EMF voltage. So that would be 15. Angle?
Yeah, which is 5.3.
532.
No, 532 angle 5.3. Don't we consider that when we are taking this to be equal?
No need phase angle because this is just magnitude. Yeah. So, and the last question F. The last question F is, if a load of 693 amperes, 0.8 lagging is connected, how much field current is required to keep the terminal voltage 830? This is non-voltage, right? So again, in this case, my IA will be still 693, right? But my current will be leading ahead. You see here, it's positive, right? Now it's positive. So my EF will be equal to V terminal plus RS plus JXS IA. Remember, IA is positive already. So from the calculation, I can get the result that EF would be 451, 7.1 degrees. You see? And my current IF, have a look at the IF, because my EF has already changed to 451. You see the EF 451? 451 is here. So my current would be, my field current would drop a lot to 4.1 amperes, about 4.1 amperes. You see? It's from here, about 4.1 amperes. Right? So from this diagram, my F will be 4.1 amperes, which means if you supply load suddenly change to capacitive load, okay? You supply load to inductive previously, but then you change it to inductive capacitive load, then your magnetizing current can reduce. You don't need that strong magnetic field. See? You see the concept has changed. If you have inductive load to your generator, you need a lot of DC current to your rotor to produce large magnetic field. But if your terminal load becomes capacitive, then you don't need that much current. You see? So induction motors, induction generators has got this sort of things. So this is just the, no much time left, so I have to stop here. And please, five minutes break. Then we come to the renewable energy section. Okay, thank you.
Midterm is still the energy storage, right?
This is the energy storage already finished. Energy storage already finished.
So midterm syllabus is still energy storage.
Oh, the midterms were up to energy, energy storage. That's right. And of course, synchronized generators. Yes?
Why not consider reactive power here?
Just 1 minute. I'll start this first. Okay. Okay, so your question is?
For the efficiency, why not consider the reactive power?
Oh, already windage, fraction and windage is already considered, right? It's already there.
But here it's just
This is all real power.
yeah.
Input real power. Output real power. Copper loss is real. Cool loss is real. And the fraction and the windage is all real.
So for the efficiency, we don't need to consider the reactive power.
No. Efficiency is only your real power output and real power input. Reactive power is the power you supply, then they will give back to you. It's the exchange of the power. That's reactive power. Reactive power only exists for inductors and capacitors, not for resistors. Okay, you got that idea? Okay. Okay. Yes,
So why is negative sign
for motors, yes.
why is
Because the torque angles are negative.
so this one is for electrical power, right? This one.
Yeah,
So this one should be output.
this output power of your generator. This is the power is consumed by your motor.
Yeah.
Yeah.
So this is input. This is output.
Yeah,
So
this is output.
Generate
Yeah, in
electrical.
terms of device there, one is input, one is output. So there's not much meaning of positive, negative. It's only,
Absorb. Or
yeah, it's I mean, if you just check through the phasor diagram, so there will be no problem. Okay, see? All right? Okay. Yeah.
Question for this one. If
Yeah.
we want to calculate the power output, can we use this equation?
The output power, there has to be three phase, yes. And yes,
So
multiply by 3.
these two equations are the same. Because this angle is...
Oh, yeah. These two equations are exactly the same because this is the calculation use terminal voltage and current. And this is calculation use your generators, like EMF, terminal voltage, and in fact, it's the same. If you remember the diagram, the phasor diagram are derived. The two heights are the same. This height, two heights, in fact, they are the power. The output power the same. So two equations are exactly the same.
Okay.
So has anybody never studied electrical circuits before? Has anybody missed out circuit analysis? Not in the university, not in the high school, never studied. Anybody? Can anybody tell me? No. So all you guys have already learned circuit analysis, right? AC circuit, you haven't? You haven't learned AC circuit, only DC circuit. Sure? You from which department or which chemical engineering? Mechanical engineering? You haven't done AC circuit? No, I don't believe it. Mechanical engineering, I used to teach. 20 years ago, I used to teach the electrical engineering course for the non-electrical engineering students. I taught DC circuit as well as AC circuit. As AC circuit, you have to use. For mechanical engineers, if you don't know AC, how can you run your motors, your induction motors, AC motors? No, you forget.
We didn't use the phasor diagrams.
Phasor diagram, maybe you didn't use very much, but the AC circuit analysis, AC power factor, you should know that, right? Yeah, okay. Yeah, depends on the lectures. Some of them don't explain the phasor diagram very much. That's true. But AC calculations, you must know it, right? You have to do it, you see. Anybody doesn't know even AC calculations?
Not really. We didn't learn much. I only had one physics unit.
You only have one, sorry?
One physics unit at university.
Yeah?
My bachelor. And it was mostly DC. And in AC, it was just knowing the basic equations.
Basic equations. We only need basic equations.
No, we didn't do any circuit analysis.
Oh, okay. But did you learn capacitors, inductance?
Yes, but I never used them.
You never
I'm a
used?
chemical engineer.
Chemical engineering. Wow, chemical engineering. Did you attend this electrical engineering course for non-electrical engineering students? You attend this electrical circuit course. I think it's electrical engineering or energy system course. Did you take that?
No, I studied in Argentina. I studied in Argentina.
Oh, you come from overseas. Okay.
Yeah.
Then you have to talk to your lecturer in Argentina.
Well, I never
Why you don't
used
teach
them,
me AC?
But I never used them at work.
Oh,
I worked
okay.
for 3 years
years that I never
Okay.
used it.
Chemical engineering, you don't use AC circuit. But you have a lot
No.
of, you
We
have a,
process engineering. It's other type of problems.
yeah, I know you
Don't
have,
focus on that.
you have a lot of devices, you have a lot of machines, they are using AC.
Yes, but we don't.
You will not,
We don't calculate anything.
okay.
Regarding that, someone else.
Okay, so that's the problem of the educational system.
Educational system.
Yeah. We,
No, I don't think
I
it's
think
a-
career paths, because as a chemical we don't need that.
No, we don't use it.
Yeah, yeah.
Why?
you
Why
do?
would we learn something that we don't?
Yeah. Do you use at home?
No.
No.
You use at home the AC
I know,
switch?
but I don't use
You
it. I
usually
don't.
buy, no, yeah, like chemicals, as a chemical engineer, you just calculate like how big the pump you need.
Yeah.
But you don't calculate if the energy supply is enough.
We don't calculate inverters, controllers.
Okay.
Different focus of the same
We
problem.
Okay.
may see what instrument we need
Yes.
and the
Yeah.
control
Okay.
system.
Okay.
We don't calculate it.
Okay.
That's not what we do.
All right. I receive a lot of feedback from you guys. I will definitely report to our department when we design this course next year. We may add up the first lecture or two to review and electrical circuit and AC circuit. It gives you some, brief explanation. Otherwise, the foreign courses would be so difficult for you guys, Later on, this course will also discuss about the load flow in the smart grids and how to calculate the power, short circuit power. Wow, I really don't know. I mean, you have very tough work for this course, okay? Anyway, but remaining lectures from me will be so easy for you guys. All right? I wouldn't use a lot of equations, not a lot of theoretical analysis, but just some idea about renewable energies, okay? All right, so firstly, question, the solar power. Well, how big is solar power? Is in the air? I mean, this is something you learned before, right? You experienced before. If we have ellipse, okay, then this is the question. It just blocked the whole America for 1 minute. How much solar energy was blocked by the moon? These two guys also were very interested in this, okay? So can you calculate it? Okay, anyway, you can do it. Okay, later on with just some concepts, okay? So we want to know some, okay, not every renewable energy sources, okay? And also we will see the principle of hydroturbine efficiency, so some basics, and nuclear power. This is all some of them we discuss in the course. May not be exactly renewable, but they are replacement for the coal power stations. Just reduce the green gas effect, see? Okay, some references you can read. I mean, this topic is really so big. If you guys want to do some investigation or do your PhD on this topic, you have a lot of things to do. Okay, another question. What is the difference between energy and the power? So this is some basic idea. I'll go through very quickly. Okay, so hey, energy bar, is this energy? No, this is not energy, right? Energy is the capacity of doing work, and the power is the rate which energy is used. How fast you do the work, that's your power, see? Sustainable energy, is this sustainable? When you have your lunch with this, you will last for 2 days, 3 days. You don't need to eat anything. Anyway, so basic concept is the unit of energy. For electrical engineering students, you must know, okay, when you pay your electricity bill, the electricity utilities charge you what? What's the unit?
Watt per hour?
Yeah, I mean, the electricity company send you a bill and calculate how much you need to pay, you see, on what basis? Kilowatts
Per hour.
kilowatts, not per hour. Kilowatts hour. Kilowatts hour. Kilowatts hour is the unit. Okay, the utility is charging you. So what's the meaning of kilowatt hour? Energy. It's not power. Okay, it's the energy. So 1 kilowatts, if you use for 1 hour, then that's 1 kilowatt hour, and the utility may charge you 20 cents. I don't know what the exact rate, but this is the energy, okay? And also, you can have a comparison of this. If you have a ton of oil equivalent to this, okay? So, if you have a full tank of petrol, hey, how much energy you pay? 50 liters, say. 50 liters of petrol is about 10 megawatt hour. See, about 10 megawatt hour. Then how much you would pay? You can calculate, just compare to the utilities price. Australian energy consumption. During this year, the coal, oil, gas, you see this dominant, the energy consumption in Australia is how much percentage? This is about 80-90%. So renewable energy is only about 6%, you see. So that's a big problem. Because why? Because why? You know the energy from, later on I will show you, the energy from the sun is so large, huge energy. But we, on the earth, the whole mankind, okay, only consume 0.01% of the energy received from the sun. You see, the potential for us to use renewable energy is huge. So later on we'll see that, okay? So UK energy consumption in year 2001 was equivalent to this of oil, okay? How much PJ UK consumes, you can also calculate, all right? So easy to calculate. Okay, energy power is the difference. Hey, this is the power. How fast you have the water come in. And here, the water you collected, that's the energy, see? So the power, DEDT, and the energy is the power integration with time. See, so this is some basic concept, just a review for you guys. And okay, so that this torch, only 10 watts, okay, maybe only 5 watts, not 10 watts, okay. So if your car is 50 kilowatts, this car is 50 kilowatts, you can convert it into horsepower. But if there is 50 kilowatts, then this power station actually can produce 2,000 megawatts. So the difference is huge. So the power station is our energy source. Energy difference, okay. So the density of the energies can be also found from here. Very heavy, 1 ton of coal is only 8 megawatt hour. 1 ton of oil is 10, okay, megawatt, okay. But nuclear fission, 1 gram of U-235, 25 megawatt hour. You see the difference, okay. You have to burn a lot of coal before for 1 gram of nuclear fission to produce the energy, you see. And 2 megawatts of turbine. In normal wind, the wind turbine, in 1 minute, okay, rotated for 1 minute, okay, how much power produced is only this, you see. So what you can see is the renewable energy, wind power here, the energy density, okay, the mass of energy production, it's much, much lower than our conventional energy sources, coal power, oil turbines, or even hydro turbines. See, so this is something we need to overcome. Okay, so a tank of petrol, how many kilowatt hour? 500 kilowatt hour. Okay, calculate it. Oscillate charge you every kilowatt, how much. Then you calculate how much I pay electricity. And then you calculate the price of the petrol. So then you see what's the difference. So electricity is still much, much cheaper than the petrol. Okay. Another question is how much kilowatt hours of electricity do you use at home every month? So check your bill, check your electricity bill. Okay, energy consumption in the UK in 2013. Energy consumption, most of them still petroleum, natural gas, electricity, but the others only very small percent. See, this is UK. And the UK energy consumption over this more than 10 years or 15 years. So most of them would be still here gas, you see, coal, also nuclear also. See, wind, wave, solar power is only a very small portion, but it's increasing. That's promising, right? That's a good thing to do. The diagram for renewable energy, actually, the light from the sun, PV, solar power or thermal power can be used here. Wind power will come from the sun. Without the sun, you wouldn't have wind. See, so here. And the wave power also comes from the sun. So all this power comes from the sun. And the solar renewable energy sources, wind, wave, tidal also. We would briefly discuss biomass, solar power, hydropower, and geothermal. So this is the most widely, or quite common renewable energy sources. This is Australia. Okay, so Australia. What are the energy sources in Australia? Hey, where is the hydropower? Where is the highest solar power area? So we can use the wind power. See, so all the energy distribution, the source distribution can be very different. In some locations, the wind is very strong. Okay, the whole year you got very strong wind, so you can produce wind power, or you can have wind power stations built in there. But some other places may not be very windy. See, so this is something. This is the UK. This is the UK wind power. In which area? The wind, the very strong wind, is only some area here. Okay, the remaining is very low wind. See, the wind speed is very, very important for the wind power stations. And this is the energy source in the UK for tidal. Tidal for different area, the tide is very high, and energy stored in the tidal can be used, but some other area may not be able to do. See, and this is an energy source in the UK for solar power. In the south of UK, you have a very high solar power energy source. Sorry, you're not in Australia, but Australia. Later we will see Australia. I talk a lot about UK because I used to teach at Newcastle University, UK. So this is a lot. Okay, so this is the energy sources in the UK. Biomass. Biomass is the plant collected energy from the sun, and eventually you can use them. Okay, so the biomass. And this is the energy source of hydro in the UK. Only certain area you have hydropower. Okay. The energy source in Singapore, nothing. Basically, it's nothing. So 98% come from the oil. Okay, oil or gas or liquid gas. Okay, and this all important from other countries. And the renewable is only about 2%. And when I worked in Singapore, I worked in Singapore Power for 6 years. And I had quite a number of visitors come to Singapore, and I made a joke to them. I said, you come to Singapore, do you know Singapore has got a very, very important sources, underground sources in Singapore? They said, no, I never heard about that, okay? I said, you take my car, travel around, any place you dig a hole, and you'll see some oil there. They don't believe it. But eventually, they found out, after they come to our industrial site, cable site, they found out, yes, because Singapore 30, 40 years ago, they used quite a number of oil cables. The oil cables always got an oil leakage. So the oil leakage got everywhere. Underground water is not too good, you see. So that's a joke. Of course, that's not oil source, but it's only oil contaminations. So this is Singapore. Hydropower, it comes to water cycle. Again, easy to understand, right? With the sign, you can move everything around in the whole cycle. And this is a hydropower station. And you can also use this hydropower. Okay, although very, very good tourist spot, you still can use the energy from there. And this is the hydropower station, the very first one, is about 150 years ago, okay? And this is directly related to us. Snowy Mountains, okay, Snowy Hydro. This is a 203 power station. I've been to most of those hydropower stations. Why? When I worked 20, 30 years ago, I worked at Monash University. We had a project with Snowy Mountains Hydro. And we frequently, we went there quite a number of times to the power stations to test their generators, to check whether the generator has any problems, you know. So this is a hydropower station. The dam is on the top. From that pipe, you see, very high. I mean, this height, the water height is more than 100 meters. Later on, we'll talk about that. See, it's a very big hydropower station here, 203. And this is the Tasmania hydropower station. Quite a number of hydropower stations in Tasmania as well. Small compared to Snowy Mountains. The hydropower station in Tasmania is quite small. The largest power station, the largest hydropower station in the world. Before year 2009, that was Brazil, okay? And how many megawatts? 12,000 megawatts. But from year 2009, that's China, Three Gorges Power Station. How big? 18,000 megawatts, you see. And Brazil is only 70% of the capacity of Three Gorges Power Station. See, it's a very big power station, very interesting, okay? If you have a chance, I would recommend you to go to Brazil or China to visit the power station, hydropower station. It's awesome, okay, the whole dam. This is a Three Gorges power station, hydropower station, all right, very, very big. This is the hydropower station, right, schematic diagram. So the water come in, kinetic energy come in and drive the hydro turbine. So your generator is on the top, so produce electricity, and the water come out to the load stream. See? Oh. So the advantage of hydropower station, renewable, clean energy, okay, domestic energy sources, okay, also generally available as needed. It can be used as a peak load, right? I discussed before, and it provides recreation opportunities as well, because you go to the dam, you can sail, you can take a cruise, you can swim. It's very good, you know. So water supply and also flood control as well. Very, very important hydropower station. Coal-fired hydro power station efficiency also very different. This efficiency is only 35%. You know, waste a lot of energy, see? But here, in hydropower station, 95%. See? Very interesting, very good. The possible environmental impact for the hydropower station, hydro energy is this list, okay? But may not be that serious, but some of them may be solved by the other way. Important features of hydropower plant meet the peak load demand. You see, this is something we discussed before. Okay, you can save a lot of energy as well. Just wanted to tell you a story. Tasmania Hydro has the hydropower stations. I said small hydropower stations. So Tasmania Hydropower Station, the energy cannot meet the demand of the Tasmania customers. See, so they have to use the cable link to Victoria. So a lot of power comes from Victoria, especially when the water height in the dams in Tasmania is lower. So they can't produce a lot of power. They need a lot of power from Victoria. Victoria has got coal power stations, oil power stations, you know. But 2 years ago, suddenly the cable connected between Tasmania and Victoria, the links broken because the cable failed. And it took more than 1 year to fix up the submarine cable. And over that year, Tasmania Hydro lost too much money. Why? Do you know why? Because they still need to supply power to the customers, right? They can't stop it. But they don't have enough energy. What did they do? They had to run diesel generators. Okay? That would be very expensive, you see. They lost a lot of money. Okay? So this is the important thing is hydropower station has got some limitations because it leaks water. Okay. In the summer, in the spring, it may be a lot of water. But in the winter, not much water, not much rain. So you don't have water, your energy will be limited. So hydropower station meet a big demand. And this is type of hydro turbine. This I'll skip, I'll go through quickly. The hydro turbine has different types of hydro turbine. Okay, the pulse turbine. Okay. Or reaction turbines, or in general, impulse turbine is easy to manufacture and cheaper. And also the soup, they only be used for high heights, high water heights, so in certain situation. So impulse turbine, so in water will the operation to the turbine is different from reaction turbine. Reaction turbine would completely immerse in the water, but the pulse turbine is the water ejection. Okay, the water jet will be hit the basket to run the turbine. So this is the impulse turbine. So water goes into and run this turbine or turbine, you see. And this is four jets. Okay. This is large turbine. Okay, so this is called a large Francis turbine. Okay. And this turbine, the water actually is, the whole turbine is immersed in water. And this is for the large turbines. Okay. For the impulse turbine, it's only for small energy. But large turbines, you need to use this type of hydro turbine. So what I can see is turbine range of applications. The flow rate, if your flow rate is very high, you could use the Kaplan turbine or Francis turbine, that the whole turbine immersed in the water. But for very high height, if your dam is 100 meter high or more, then you can use the impulse turbine. Otherwise, low flow, low height, you would need to use Francis turbine. Okay. So this is the difference. High height, 100 meters or higher. See, you can use the impulse turbine. You can use the impulse turbine like this, like Snowy Mountains, 2 or 3 power station. They can use this turbine. It's impulse turbine. For medium height, you could have a combined impulse or Francis. And for the low height, you would have this Francis turbine. Okay, the whole turbine is immersed in the water. Okay, efficiency of hydro turbine is the output power divided by your total energy stored in the water. So typical losses, okay, due to fractions, the influence of the water. So the whole efficiency can reach to 95%. Very good turbine, you can get that. Okay, normally it's only 80 to 90%. The energy in the water, the total energy can be calculated by this. Okay, the potential energy can be calculated from these mg high. So that kinetic energy is this equation. You can calculate. Energy in the water can also be calculated by this equation. The pressure energy, the ratio of energy divided by weight is the height. The ratio of energy divided by weight is called height. Means the height is not the height of the dam. It's the ratio between the energy you store and the weight of your water. See, it's calculated by this equation. So it's not the height. It's not only the height, but also the two other terms determine the height of the water. So hydropower calculation use this equation. Okay, use this equation. You have flow, you have all these things. Okay. Examples: consider a mountain of these. So efficiency, the height of 25 meters and flow rate is how much power could a hydrogen generator say? So in fact, it's all very simple examples. Very simple examples. After you read through, you can do it. You can make a quick calculation for this. Okay, hydropower, the advantages and drawbacks. Okay, it's a positive. It is very renewable sources, right? So no contamination. Okay, big scale can go to very, very large power station. And the negative is it could affect the environment. Okay, it could have some impact to the local area. Okay, so very high initial cost to build up the dam. So this is it. Okay, the next one is nuclear power. Nuclear power production of electricity by nuclear fission. The impact of nuclear power causes the fission process, which comes some byproducts as well. You can produce heat, and also the waste of nuclear power station is also a problem in most cases. So nuclear fission produce heat from the boiler. Okay, from the boiler, you can generate a high temperature, high pressure steam. Then you can drive that steam turbine. See, very simple, very simple, very similar to other thermal power stations. Control of the reaction, the chain reaction, control reactions. Okay, I believe you guys read already some magazines. It's already explained to you how to control the fission. Okay, use the control rods. Okay, you can control the reaction. See, and this is the production of uranium, mining, refining. Okay, a lot of process before you can produce something which is used in the nuclear power station. This is a compound of commercial reactors. This is commercial reactors. Okay, the cores and compressed facial. It's a very complicated system and a lot of safety issues. honestly speaking, I've never been to a nuclear power station. Although I think it's not easy to go in because a lot of security reasons. So, okay, the fact of nuclear power is not renewable, but compared to the other energy sources, it produces less contamination. 6% of global energy production, more expensive than the other power generations. Okay, because the initial production, the cost, okay, the construction costs, radioactive waste is also a problem. Okay, so this is a nuclear power station. The main problem of nuclear energy is cost, safety, another thing, okay, waste disposal, all this sort of thing related to nuclear power station. A very promising nuclear energy source is nuclear fusion. Okay, nuclear fusion have no problem with the waste. See, so that's very, very, very interesting, very good. It's great challenge that we can have a lot of energy produced, and also it would be 2.5 pounds of nuclear materials to produce the same energy of the power, and it will emit only 2 pounds of helium. So very, very little pollution. So the technology is very good. But technology at this moment, controllable fusion, is not successful yet. Okay, in the laboratory maybe even very, very later scale, but it's not complete use. So energy from nuclear fusion in the sun is huge. So every minute, how much material? Okay, it's 5 million tons of materials. Okay, are converted into energy every second. See, so how much energy is produced by the sun? So it's unbelievable. It's really big. So this is the first part of the renewable energy. As I said, it's really an introduction about the energy sources, renewable energy sources. And from the lecture slides, you can, and also in the Moodle, you have a lot of references. Okay, you can read a lot of references. But this course is just to cover the general idea for this. The most important thing is to understand the smart grids, the generators, turbine generators. Okay. So next week again, come here, turn to the line. Okay. You will before you enter to the theater, the examination paper will be already put on the seats. Okay, you have a seat, so you will just sit in with your pen, your pens, use your calculators. Okay, whatever. Only these things, no other materials. Okay, you have no paper to bring. Just sit down in. Then we will start exactly at 9 o'clock. All right. Then you will have 1 hour. If you come in late, no way. You would be.
No formula sheet?
Sorry?
No formula sheet.
Sorry, can't.
Will
you provide any
be given any
formula sheet?
Oh, and the formula. Okay, I will. I'm so kind to you guys. I provide you 2 formula.
Only 2.
Only 2 formula you need to use. But the other formula you can remember. You see, you can remember yourself. You know. But of course, all the power electronics, you'll be given quite a number of equations, formula, and all the other things.
So
all
the
right.
formula required you already all give.
Yeah. You will be given many equations.
Similar to the one that they got last year?
Sorry.
Is it similar to the one they got last year?
Yeah, similar. You have multi-choice questions. You have 4 multi-choice questions.
Like this
Yes.
page?
Yes, something like that. Something like that. The formula, something like that. Okay? But still remember the basic equation. Okay, don't ask me, hey, I forget basic equations. Yep. No, no question.
Can you help
Yes,
me with this one, please?
Which one?
This a three-phase synchronous generator produces an open circuit line voltage.
Okay,
It
yes.
means the circuit is open, no load is connected. And since
Yeah.
it's a generator, if we draw it, it's open here.
Yes.
Nothing connected.
That's connected, yeah.
So the VT here is 6920 volts. Right?
Line voltage.
Because it's the line voltage, but if
Yeah.
we want to convert to phase, it's...
Yes.
But this is the VT here.
Okay, correct, correct.
When the DC exciting current is, IDC is 50 amp, the AC terminals are then
Okay.
short-circuited and the three line currents are found to
Yeah.
be.
Yeah.
So I phase is found to be 800. Assuming that this is a Y-connected system, I'm assuming.
Yes, yes. You can.
Then we have to find the synchronous reactance per phase. So,
You have a very simple
okay.
equivalent
So
circuit.
this is my total phase current.
Total
So
phase current.
per phase, it's the same, right? Because for Y, phase
For
current,
same
line
current,
current is the same.
every phase current will be exactly the same.
Same.
Yes,
So
the
I
balance
just-
is three phase.
I just use EF is equals to VT plus JXSIA. IA is 800. VT is 6920 by root 3.
Yeah.
But then what about my EF? I don't know.
Calculate from this equation.
But then I have to find the synchronous reactance first.
Synchronous reactance is being given, right?
Nah, this is
No,
the...
it's three-phase synchronous generator. Open circuit line for this. When the DC exits this, the AC terminals
Are then short
and then short
circuited.
circuit.
And the
Okay.
three line currents are found to be
Yeah,
this.
yeah. When you use short circuited, which means your terminal voltage is zero, right? You don't have, but when you open circuit, your terminal voltage is exactly the same as your EF. See? Because you open circuit, the terminal voltage, you don't have current go through this reactance.
So open circuit, VT is equals to
EF, that's right.
EF and IA is equals to 0.
Yeah, I is zero. Then you
So
short
this
circuit.
EF is this.
Yeah,
But then when we short circuit, we just have the current and what
zero.
Oh, VT is 0.
Zero.
Short circuit VT is there.
Yeah, it is zero. Correct.
Excuse
And
me.
current
You-
is 8.
Can we set up?
Oh, sorry.
I am
Sorry,
so
we must
sorry.
go.
No worries,
Sorry,
no worries,
it's
it's
my
not
fault.
mine. Thanks.
Sorry.
No, it's all right.
Thank you very much. See you. Thank you.
So when we then bought a FIP system afterwards, part of the decision was based on the service contract fees, and their size was simply a factor of 2 cheaper than FEI, which was the main reason that at the end we went with the size of scope, which I'm not really happy with, but I think the operations, I find it annoying, really annoying. People are having a fairly hard time to adjust from working from the FEI system to the size system. It took much longer than I ever expected to train people to use it.
Yeah, and that's. I mean, as much as I don't like being a single instrument lab, symbol maker, because it looks, doesn't look good in some ways. The training issue is big.
Yep.
So the training people from the Donna 200 when they're technically competent is actually just like often starting again.
Yeah.
Which for me, I find that I have real trouble. The power's down here. I have real trouble coping with that. because I guess when I learned the microscopes, I learned all sorts of microscopes at the same time, and I never had any trouble